Hello out there, welcome to this tutorial on complex numbers. First, we look at definition, the real numbers. The numbers 3, -9, 0.25, 0.333, this is a recurring decimal, pi, root 5, etc. are real numbers. This is said to be the second largest set of numbers. Also, we look at the imaginary numbers. The numbers square root of -4, square root of -9, square root of -5, and so on give birth to another set of numbers. I, -I, 3, -2i, and so on are called imaginary numbers. The fact that we cannot find the exact value of square root of -4, -9, or -5 by any mean, that gives birth to the set of number I, where I is square root of -1. So since we cannot find the exact value of square root of -1, it is represented by I, and this I is called imaginary number. So that from here we can have square root of -4. Since -4 can be written as 4 times -1, so we have it as square root of 4 times square root of -1. And we all know square root of 4 to be plus or minus 2. And this root of -1 is I. Here, the square root of -9 can be written as positive or negative 3i, and so on. These are called the imaginary numbers. Then the complex numbers. The complex numbers is the largest set of numbers because every real number can be written as complex number. We now look at the definition. The number represented by z is equal to a plus bi is called the complex number, where a is the real part and bi is the imaginary part. So you can see the real number plus or minus the imaginary number give birth to the complex number. Examples are, we have 2 plus I, where 2 is the real number and I is the imaginary number. We have pi minus 3i, where pi is the real part and the 3i is the imaginary part, and so on. Like we said earlier, the complex number is the largest set of numbers. Like here now, if I have 2 plus 0i, which means it is 2. That's real number, but the imaginary part is 0. We can also have another complex number whose real part is 0. So these are what we are going to be looking at here. Now in our next slide, we'll be looking at powers of imaginary numbers. So we have I raised to power 2. We know I is square root of -1. So I squared is square root of -1 times square root of -1. And that will give us -1. Then we now have I raised to power 3. This is I squared times I. So we know that I squared is -1, then multiply by I, and that gives -I. Then also we have I raised to power 4. I raised to power 4 can be split into I squared times I squared. And we have I squared to be -1 times -1. And that gives +1. Then we look at I raised to power 5. I raised to power 5 is I raised to power 4 times I. Remember our law of indices. This is I raised to power 1. Since we are multiplying, we add. So I raised to power 4 is positive 1, then times I, and that gives I. We now look at I raised to power 15. Now, how do we get this very large number? If we have a very large number like this, we divide 15 by 4. When we divide 15 by 4, we are going to have 3 remainder 3. Since we have 3 remainder 3, so the quotient is 3. We multiply it by 4, it gives 12, then plus the 3, which means we can write I raised to power 15 as I raised to power 12, then times I raised to power 3. Or we can just look for multiple of 4. The largest multiple of 4 we can get from 15, which is 12, and we then add 3 to make our 15. We can then write this as power of 4. That's going to give us I raised to power 4, then raised to power 3. Still applying law of indices, I raised to power 4, then all to the power of 3, we just multiply the indices, then times I raised to power 3. Okay, we just split this into this by application of law of indices. Then from here, we know I raised to power 4 is positive 1. Then we now have it as raised to power 3, then times negative I, since I raised to power 3 is negative I. So 1 raised to power 3 is 1. Multiplied by negative I gives negative I. Then for our information, we can now look at it from the general point of view that in general, for power n, where n is greater than 4, I raised to power n is equal to 1 if 4 divides n and leaves no remainder. Okay, like we saw in I raised to power 4, or we have it as I raised to power 12. Since 12 divided by 4 gives 3 without remainder, what we just do is we have I raised to power 12 to be equal to 1. Then also I raised to power n is equal to I if 4 divides n and leaves a remainder of 1, can only leave a remainder of 0, 1, 2, and 3. It cannot leave a remainder of 4. So if 4 divides n and leaves a remainder of 1, then I raised to power n is I. Then also, I raised to power n is equal to negative 1 if 4 divides n and leaves a remainder of 2. For your information, you still remember I raised to power 2 is negative 1. Okay, I raised to power 2 is negative 1, since the quotient will always multiply 4 to give you a positive 1. Then multiplying it by whatever power of I that is remainder. So since I raised to power 2 is negative 1, then multiplying it by 1 will still give us negative 1. And lastly, I raised to power n is equal to negative I if 4 divides n and leaves a remainder of 3. We saw that I raised to power 3 is equal to negative I from our previous slide. So the quotient times 4 to the power of I will always give us positive 1. So it is this remainder now that will now determine the value of I raised to power n. So that is it for powers of imaginary numbers. Then we now look at some basic operations on imaginary numbers. Then here we go. Evaluate each of the following. A, 2i plus 4i. B, 3i minus 7i. C, 5i times 2i. And D, 15i divided by 3i. I. So in our solution, we start from A 2i plus 4i, and that's going to just give us 6i. It is as good as saying 2x plus 4x, which gives 6x. So the same thing here, 2i plus 4i gives 6i. Then for B, we have 3i minus 7i. 3i minus 7i, 3 minus 7 gives negative 4. So 3i minus 7i gives negative 4i. Then for C, we have 5i times 2i. So what we do here now is collect the coefficient of the i's. That's 5 times 2. 5 times 2 gives 10. Then we now have I times I. So since 5 times 2 gives 10 and I times I gives negative 1. So 10 times negative 1 gives negative 10. Then we go for D. 15i divided by 3i is just going to give us 5. You know why it is 5? Because we have 15 divided by 3, then times I divided by I. 15 divided by 3 is 5, and I divided by I gives 1. So we have our final answer as 5. So this is the highest we can take on basic operations on imaginary numbers, and any other value we follow the same pattern. We now go to basic operations on complex numbers. So here we go. Given that z1 equals 2 minus 3i and z2 equals negative 3 plus 4i, evaluate A, z1 plus z2, that is addition of complex numbers. B, z1 minus z2, that's also subtraction of complex numbers. C, 2z plus z1, this is scalar multiplication of complex numbers. D, z1 times z2, multiplication of complex numbers. And E, z2 over z1, this is division of complex numbers. So we start the solution of the problems. From our solution, we start from A. For A, we have z1 plus z2. So we can carry out our addition in a tabular form. It could be multiplication in a tabular form. So z1 is 2 minus 3i. So I have 2 minus 3i. Then plus z2, which is negative 3 plus 4i. We then add in a tabular form. So starting from here, 2 plus 3i. So what we do here, in our addition, we add the real parts and also add the imaginary parts. So we have for the real part is 2 plus negative 3. Remember, positive times negative gives negative. So 2 plus negative 3 gives 2 minus 3, which gives negative 1. Then also we have the imaginary part, which is negative 3i plus 4. This is plus 4. That will give us plus 4. So negative 3 plus 4 gives 1. So we have our answer there as plus I. That's the end of solution to the addition of z1 and z2. Then we go to B. So for B, we have z1 minus z2. Also arranging the subtraction in a tabular form, we have 2 minus 3i minus negative 3 plus 4i. Again, we are going to subtract the real part and thereafter the imaginary part. So from here we have the real part to be 2 and negative 3. So that 2 minus negative 3 here, since negative times negative gives positive, 2 minus negative 3 is the same as 2 plus 3, and that gives 5. Then also we go to the imaginary part. So we have negative 3 minus positive 4, which is the same thing as minus 4. Then we say minus 3i minus 4i, and that gives negative 7i. So we are done subtracting z2 from z1. Then we go to the C part. For C, we have 2z plus z1. First, we simplify 2z2. How do we do that? We just multiply z2 by 2. That's going to be 2 into negative 3 plus 4i. 2 times negative 3 gives negative 6. And 2 times 4i gives positive 8i. Then going by our summation now, we have 2z2 plus z1. Our 2z2 is negative 6 plus 8i, then plus z1, which is 2 minus 3i. Then we carry out the addition as we did in A. So the real part, that's going to give us negative 6 plus 2. Negative 6 plus 2 will give negative 4. So we have negative 4 for the real part. Then for the imaginary part, we have 8i plus negative 3i. So this is going to give us 8i minus 3i, which gives plus 5i. And that is all for the C part of the problem. We go to the D part. For D, this is multiplication. Z1 multiplied by Z2, and that's going to give us Z1, which is 2 minus 3i in bracket, multiplied by negative 3 plus 4i, which is the Z2. It is just as good as the algebraic expansion that we know. So what we do is we pick this the real part and use it to multiply every other part in the second bracket. So we have it as 2 into negative 3 plus 4i. Then thereafter, we pick this, the imaginary part. We use it to multiply every part of the second bracket. So we have it as negative 3i into negative 3 plus 4i. Then we expand and simplify. 2 times negative 3 gives negative 6, and 2 times positive 4i gives positive 8i. We are done with this part. Then we go to the other part. Negative 3i times negative 3 gives positive 9i. Then negative 3i times positive 4i. For your information, negative 3 times positive 4 gives negative 12. Then I times I gives negative 1. So that negative 12 times negative 1 gives positive 12. Then we simplify the real part and then the imaginary part. This is negative 6 plus 12, and that will give us a 6. Then positive 8i plus 9i gives positive 17i. That's the end of solution to the product of Z1 and Z2. Remember, it could be written as Z1, Z2. So whatever you see there, it is going to be product. So we go to the E part of the problem. For E, we have Z2 divided by Z1. So we are going to have it as Z2, which is negative 3 plus 4i over 2 minus 3i. That's what we call the conjugate of complex numbers, like we saw in the conjugate of binomial surd. What we just do is to make the denominator a real part. And the only way we can do that is to multiply this denominator by the conjugate of this complex number. How do we get the conjugate of Z1? Since the connector here is negative, so its conjugate will just be positive. So if the connector is positive, its conjugate will just change to negative. Like for Z2, the conjugate of Z2 is going to be negative 3 minus 4i, while the conjugate of Z1 is 2 plus 3i. So that is that for z1 and z2 conjugate. So coming back to our problem, we are going to multiply the numerator by the conjugate, which is 2 plus 3i. So we have multiply by 2 plus 3i over 2 plus 3i. So whatever you do to the numerator, you also do it to the denominator in order to balance everything, because this is as good as multiplying by 1, which does not add any value to the expression. So doing that, we have negative 3 plus 4i times 2 plus 3i over 2 minus 3i into 2 plus 3i. The expansion of the numerator is going to be like what we did in D. Why the expansion of the denominator? Because they are conjugates of each other. We just multiply the real part and the imaginary part. We then conclude that expansion. For the expansion of the numerator, I pick the first part, that is the real part in the first bracket, and use it to multiply everything inside the second bracket, so that we now have negative 3 times 2 gives negative 6, and negative 3 times positive 3i gives negative 9i. So we are done with that. We pick the second part of the first bracket, which is the imaginary part, that is plus 4i. We use it to multiply everything inside the second bracket. So positive 4i times 2 will give us positive 8i, positive 4i times positive 3i. Remember, 4 times 3 gives 12, and I times I gives negative 1. So 12 times negative 1 gives negative 12. Then over, what we are saying is, for the expansion of the denominator, as we explained earlier, we multiply out the real part and then the imaginary part. We said we are multiplying 2 by 2, and the imaginary part, which is negative 3i times the positive 3i. So we multiply out and simplify. So we have 2 times 2, which gives 4, and negative 3i times positive 3i. Negative 3 times negative 3 gives negative 9, and I times I gives negative 1. So negative 9 times negative 1 gives positive 9. So we then simplify and have our final answer for the division of the complex numbers. So this is negative 6 minus 12 gives negative 18, and negative 9i plus 8i gives negative I, then over 13. And that's all for the division of Z2 by Z1. So we are done with basic operations on complex numbers. We then go to the complex plane. For the complex plane, we know our Cartesian plane is a plane of x and y axis. So in the complex plane, the horizontal axis is going to be the real axis, while the vertical axis is the imaginary axis. So here, their intersection will still remain the origin. So to the right, we can have it as real positive part, and to the left is the negative part. So here, this is the positive, here is the negative. So calibrating, if you take each one as one unit, here is going to be negative 2, negative 4. This is 2i, 4i, and here is negative 2i and negative 4i. This is the complex plane. So the next thing is, how do we plot the complex numbers on the complex plane? So we go here. On a complex plane below, this is the complex plane, plot each of the following. We have z1 to be 3 minus 2i. We have z2 to be -1 plus 3i, z3 to be -I, and z4 to be -3. Starting from A, we have the real part to be 3 and the imaginary part to be -2i. So here, on the real part, this is 3. This is the line where the real part is 3. Then for the imaginary part, we have -2i. Here is the line where the imaginary part is -3i. Their point of intersection is this, and that will represent our z1. So that is the point for z1 on the complex plane. Then for z2, that is the B, the real part is -1. This is the line where the real part is -1 and the imaginary part is +3. This is the line, the imaginary part is +3. Their point of intersection is here. So we label that point as Z2. So that is the Z2 on the complex plane. Then for Z3, the real part here is 0. The Z3 can be written as 0 minus 4i, where the real part is 0 and the imaginary part is -4i. So where do we have the real part to be 0 in the Cartesian plane? It is the imaginary axis. And where we have the imaginary part to be -4 is this line. So we have the line here and their point of intersection is this. And that will give us the point Z3 on the complex plane. Then finally, we have the Z4, which is the part of the problem. This can also be written as -3 plus 0i. In the earlier stage of this lesson, we told you that complex number is the largest set of numbers because even the real number is a complex number with imaginary part to be 0. This is a typical example we have in Z4. So -3 plus 0i. So which means the real part here is -3 and the imaginary part is 0i. So the real part is -3 has this line here. This is the line where the real part is -3. Then the imaginary part being 0 is the real axis. So their point of intersection is here. So we have our Z4 on the complex plane as this point. So that is all for the complex plane and how to plot the complex numbers on the complex plane. And this is the highest we can take in this tutorial. I hope you enjoyed it. Please like and share this video. Until we come your way again, goodbye.